We now discuss the picture that quantum mechanics gives for atomic structure, a picture that supersedes the Bohr model. The Bohr expression for the radii and energy levels of the hydrogen atom can be applied when a single electron orbits the nucleus, whereas the theoretical framework of quantum mechanics can be applied, in principle, to atoms that contain an arbitrary number of electrons. The picture of the hydrogen atom that quantum mechanics and the Schrödinger equation provide differs in a number of ways from the Bohr model. In the Bohr model, the energy is specified by a single number, n. Because this number can have only discrete values, rather than a continuous range of values, n is called a quantum number. Therefore, the energies of the hydrogen atom in the Bohr model are specified by just one quantum number, n. In contrast, quantum mechanics reveals that 4 different quantum numbers are needed to describe each state of the hydrogen atom. The 4 quantum numbers are described as follows. First is the principal quantum number n. As in the Bohr model, this number determines the total energy of the atom and can have only integer values, n equal 1, 2, 3, etc. In fact, the Schrödinger equation predicts that the energy of the hydrogen atom is identical to the energy obtained from the Bohr model, or En equals negative 13.6 electron volts times z squared divided by n squared. Next is the orbital quantum number L. The values of L depend on the value of n, and only the integers L equals 0, 1, 2, 3 to n minus 1 are allowed. This number determines the angular momentum of the electron due to its orbital motion, the magnitude of which is given by L equals the square root of L times L plus 1 times h divided by 2 pi. The orbital motion of the electron can be loosely compared to the motion of the Earth about the Sun. There is something a bit peculiar, however. For example, if n equals 4, then L can take values 0, 1, 2, or 3. When L equals 0, the magnitude of the orbital angular momentum is 0, which is not allowed by the Bohr model. Recall that the orbital motion of the electrons about the nucleus was brought forth in part to counteract the Coulomb attraction between the negatively charged electrons and the positively charged nucleus. The fact that the quantum picture allows 0 orbital angular momentum should be an indicator of the relatively unintuitive or peculiar nature of quantum physics. Next is the magnetic quantum number, ml. The allowed values of ml depend on the value of L, with only the following positive and negative integers being permitted. The word magnetic is used here because an externally applied magnetic field influences the energy of the atom, and this quantum number reflects how the external field affects the energy levels. Since the effect was discovered by the Dutch physicist Peter Zeeman in the early 1900s, it is known as the Zeeman effect. When there is no external magnetic field, ml plays no role in determining the energy. In either event, the magnetic quantum number determines the component of the angular momentum along a specific direction, which is called the z direction by convention. The z component of the orbital angular momentum is quantized, and its magnitude is given by Lz equals ml times h divided by 2 pi. Finally, the 4th quantum number is the spin quantum number, ms. It can only take values of plus 1/2 or minus 1/2. This number is needed because the electron has an intrinsic property called spin angular momentum. Loosely speaking, we can view the electron as spinning about its own axis while it orbits the nucleus, analogous to the way the Earth spins as it orbits the Sun. The phrases spin up for plus 1/2 and spin down for minus 1/2 are often used to refer to the directions of the spin angular momentum associated with the values for ms. This table summarizes the 4 quantum numbers that are needed to describe each state of the hydrogen atom. One set of values for n, L, ml, and ms corresponds to one state. As the principal quantum number n increases, the number of possible combinations of the 4 quantum numbers rises rapidly, as we will now see. We start with the case of n equals 1. The orbital quantum number L can take integer values from 0 to n minus 1, which, in this case, only allows L equals 0. The magnetic quantum number ml can take integer values between plus L and minus L, for which again only leaves 0 as a possibility. Finally, the spin quantum number ms can take values of plus 1/2 or minus 1/2. We can now identify the allowed quantum states with a sequence of 4 numbers, n, l, ml, and ms. Therefore, in this case with n equal 1, we have only two possible states, 1, 0, 0 plus 1/2, and 1, 0, 0 minus 1/2. Now let's look at the case of n equals 2. The orbital quantum number L can take integer values from 0 to n minus 1, which in this case allows L equals 0 and 1. The magnetic quantum number, Nl, can take integer values between plus L and minus L. For L equals 0, Ml can only be 0. For L equal to 1, Ml can take on values minus 1, 0, and plus 1. Finally, the spin quantum number Ms can take values of plus 1/2 or minus 1/2 for each Ml value. We can now identify the allowed quantum states with a sequence of 4 numbers, N, L, Ml, and Ms. Starting from the top, we have 2, 1, 1 plus 1/2, then 2, 1, 1 minus 1/2. Next, it's 2, 1, 0 plus 1/2, and then 2, 1, 0 minus 1/2, and so on, accounting for all possible states. For n equal to 1, we only had 2 possible states. For n equal 2, we have 8 possible states. For n equal 2, all of these states have the same energy when there is no external magnetic field. According to the Bohr model, the nth orbit is a circle of radius Rn, and every time the position of the electron in this orbit is measured, the electron is found exactly at a distance Rn away from the nucleus. This simplistic picture is now known to be incorrect, and the quantum mechanical picture of the atom has replaced it. Suppose that the electron is in a quantum mechanical state for which n equals 1, and we imagine making a number of measurements of the electron's position with respect to the nucleus. We would find that its position is uncertain, in the sense that there is a probability of finding the electron sometimes very near the nucleus, sometimes very far from the nucleus, and sometimes at intermediate locations. The probability is determined by the wave function psi, as section 29.5 discusses. We can make a three-dimensional picture of our findings by marking a dot at each location where the electron is found. More dots occur at places where the probability of finding the electron is higher, and after a sufficient number of measurements, a picture of the quantum mechanical state emerges. Here we show the spatial distribution for the position of an electron in a state for which n equals 1, L equals 0, and Ml equals 0. This picture is constructed from so many measurements that the individual dots are no longer visible, but have merged to form a kind of probability cloud whose density changes gradually from place to place. The dense or darker regions indicate places where the probability of finding the electron is higher, and the less dense or lighter regions indicate places where the probability is lower. The radius where quantum mechanics predicts the greatest probability per unit radial distance of finding the electron in the n equal 1 state is here. This radius matches exactly the radius of 5.29 times 10 to the negative 11 meters, found for the first Bohr orbit in the Bohr model. For a principal quantum number of n equal 2, the probability clouds are different than for n equal 1. In fact, more than one cloud shape is possible because with n equal 2, the orbital quantum number can be either L equals 0 or L equal 1. Although the value of L does not affect the energy of the hydrogen atom, the value does have a significant effect on the shape of the probability clouds. Here we show the cloud for n equal 2, L equals 0, and Ml equals 0, which is more complex than that for n equal 1, but still spherically symmetric. However, when n equals 2, L equals 1, and Ml equals 0, the cloud has a two-lobed shape with the nucleus at the center between the lobes. For larger values of n, the probability clouds become increasingly complex and are spread out over larger volumes of space. The probability cloud picture of the electron in a hydrogen atom is very different from the well-defined orbit of the Bohr model. The fundamental reason for this difference can be traced to the Heisenberg uncertainty principle.